Now let's dive into another data set in this building data genome project to look at a few more examples of how to use pandas, functions, and data cleaning, etc., to analyze meter data. So we're going to we just looked at comparing energy data of different buildings. Now let's look at weather influence on energy consumption. I've already done this. I've created this notebook and I've spun it up in my Kaggle account. We want to look at how does weather influence buildings. In hot climates and cold climates, theoretically, as it gets much hotter or much colder, you should see an increase in energy consumption. It's just logical, since that there are air conditioning and heating systems that are probably powered by some form of energy. So let's do this analysis, take a look, and learn some pandas at the same time. So of course we load our library of pandas. We're going to load our electricity data once again, the non-cleaned version. We're going to look at a .info here. Once again, this is similar to what we saw before. Skip over this line of code here. But this one, what we'll do is create a data set of buildings from the Panther data set that are also offices. You can see here, this is a fancy bit of code here, which is using .loc to detect and to filter the columns in this data frame to find the ones that are both Panther data set and office buildings. We use the ampersand sign here. We put these conditionals in parentheses, and you're able to do this. We're also going to truncate and look at just 2017 data. If we look at this data set, what we have is 24 buildings, 8760 entries, of course, hourly data. There is quite a few buildings that have most of the data, not all of the data, a few gaps here and there. If we plot this data for this year, what we're going to see is we're using subplots equals true. Therefore, it's going to show us time series line chart for each of the buildings themselves. What we see is, here are the line charts. Here you can see Office Hannah, Office Catherine, Office Patty, Office Loretta, Valerie, Carla, Graham. Okay, so you get the point. There's a lot of these here. You can really see some of the patterns and behaviors. You see Office Kristen just has this drop off across 2017. Antoinette has this weird behavior here. You have shifty behavior here with Kristen, and Brent has some missing data there. You can see all kinds of different information from looking through those visualizations. So of course, we're going to look at how does weather influence the consumption of some of these buildings. To do that, what we need to do is load a weather data file. So in the data set itself, there is a bunch of energy data. There's also the metadata file, which we've been using. There's also a file called weather.csv. And this file is, what we'll do is we'll load this file. We're also going to use the timestamp column. We're going to parse states equals true. We're going to look at what's in that data set. This data set is unpivoted, which means that we have the site ID we have over 330 rows in this data frame. And one of those rows is site ID, which means that we don't need this entire data set. We just need the site of Panther. So what we'll do for this site data, we'll filter out where the site ID is equal to the word Panther, which will give us a data set which is much smaller. It's just the Panther data set. You can see if we plot it, what we'll see is that it's over a 2-year period. You're seeing outside air temperature. If we plot our air temperature, which is one of the columns, you can see that it's a cooler climate in the winter. In the summer, it gets up to 30 degrees Celsius, so a bit warm. In the winter, it comes back down again. But it's a kind of a moderate climate. You'll notice even in the winter, it gets up to 20 to 25 degrees Celsius, which is nice and balmy. If you're curious where this location is, you can actually look it up in the paper. I'm not going to give away the location. I'll get you to look up the paper to find that out. So what we need to do is see and compare this data versus the data up here above from the buildings. We chose one of the buildings, this Panther office, Lavinia. Lavinia looks nice. It looks like it has like pretty consistent behavior across each of the weeks of the year. You see a little outlier here. There's maybe a bit of missing data if you zoomed in and saw some gaps. But the other thing you'll notice is that it looks like in the winter, this building is using more energy. In the early part of the year, the late part of the year, during the winter months, there seems to be an increase of energy. Let's see if we can identify that relationship. So let's come down here and look at, first thing we want to do is I want to show a little lesson in removing outliers. Look at Office Lavinia. What we'll see is, first we can look at the head of it. We see that, that we got what we need. Let's make a plot of that. Like I said, we have this weird behavior here where it's like super low value in February. And this is an outlier. So outliers can be the result of errors in the system. Maybe the meter broke. Maybe the building got shut down. Maybe there was some sort of maintenance going on. But at the end of the day, we want to understand the relationship between outside air temperature and normal behavior of a building, not outlier behavior. So sometimes you'll want to remove these outliers. And we're going to do it in a really simple way this time, just to show to begin with, the simple way. And you can learn more advanced ways of anomaly detection and outlier removal in more advanced courses or later on in this course. If we zoomed in on that little area, we do truncate to look at this outlier in early or mid-February, we'll see that we've got this weird, like really low value. There's a gap here. We want to get rid of this value. We want to try to remove that. And it's quite simple. What we do is create a new data frame _ no outlier. We basically filter everything out of this sample meter data set that is less than 10. We're pulling out what's greater than 10 and removing this outlier, which is less than 10. Like I said, this is a really simple way. We're eyeballing this and seeing, okay, this outlier is below 10 here. Let's go ahead and remove it. There's lots more advanced ways of doing this, but I want to show the simple way first. So let's go ahead and execute that. What we end up with is a data frame that if we replot it, our range is from 15 to 50 kilowatt hours for each hour, and we've removed that low point. And we can zoom back in on that little area and notice that, yeah, we've removed that outlier. There's still a bit of outlier behavior here, but it's not quite as extreme as the one that we removed. Now that we know we have some outliers in this data set. So if we look at Panther Office Lavinia, we have 8748 points. There's 8760 hours in a year. So we've removed actually at least one of those points through our outlier removal, but from the data set, there was also quite a bit of missing data already. So what we can do is, of course, use one of the techniques we learned in this series of videos, .fillNA. We're going to use the method forward fill. And what that's going to do is it's going to basically fill like this gap here with the point before. It's going to take the last point here and just move it there. And let's see how that works. So we can execute this line. We can look at .info and notice now we have a full 8760. Every gap has a point. There's no non-null values left in the data frame. Here you can see that it filled that forward from this last point. It filled that gap. This is not perfect, but it does help us in situations like this where outliers are removed. We want to utilize as much of the weather data set as possible. And these type of corrections or fills are not going to have a big impact on our analysis. There are lots of other situations for gap filling that you learned in other lessons that require something different, but in this one, we're going to keep it simple. So let's do this. Let's merge these data sets. What we'll do is let's create the temperature data set, which we will merge with our energy data set. Let's look at that temperature data. We've got 8760 objects in here that are floats, so numerical. We have air temperature, so we're ready to go. Let's use .concat to merge these two data sets. Concat is quite useful here because we have two indices for each data frame, which are exactly the same. They're identical. They're basically the year of 2017 hourly data. And concat is great for that. It's great for gluing together two data sets. One of the attributes, we have a list with the two data frames inside of it. We have the axis equals 1, which is indicating to concat that it wants it to glue together the data frames according to their columns. And when we look at the resultant comparison data frame, now we have two columns in our data frame, which are nicely added together. We can see here in our .head the first 5 rows. So we have air temperature and the energy consumption. I'll do the exact same thing using the .merge function just to show the difference in notation. Here you can see comparison _ merge. It's a different data frame that we're creating, and we're using .merge instead. And .merge has the two data frames we're trying to add together. We're using other attributes, which are more similar to what happens when you query databases. So you're able to specifically indicate where you're merging these on. So .concat just assumes you're gluing the data frames together based on the index. Here we're explicitly saying that the index, the left index, right index true is what we're merging them based on. You can merge them based on other columns as well besides the index. And we're using an attribute called how. There are different options to this: inner, outer, left. This allows the merge function to know how you're blending these two together, especially in situations where you don't have such a nice glued together situation like .concat is usually good for. So dot merge does the same thing. Here you can see the result, which is exactly the same as the others. Let's take a look at the comparison plot. We're going to use subplots equals true. Let's look at here you have the air temperature here on top, and on the bottom you have the energy consumption of office Lavinia. You can see some really interesting patterns here. As the energy consumption gets higher here on the bottom, you can see this corresponds very nicely with seemingly cold spells, like cold fronts that came through. There's a lot of air temperature reduction here, and you can see corresponding spikes in energy consumption in this building. So one way, the best way to analyze two data points to see relationships is a scatter plot. And we're going to learn a lot more about visualizations in the next upcoming section of this course. But here you're going to get a teaser of what this looks like. We're going to use dot plot. We're going to indicate the scatter type. We're going to specify the X and Y axis based on the comparison plot we're looking at, set the figure size, and voila. Here what we have is a scatter plot with air temperature on the Y axis and energy consumption on the air temperature on the X axis, consumption on the Y axis. You can see very clearly this pattern. It's quite of a diverse, sort of wide pattern here, because this is hourly data, but you can see as it gets colder, you see a definite trend to the left going upwards. So the colder it is, the more energy consumption the building is using. To make this a little easier to see, we can get rid of some of the noise by resampling to daily data and taking the mean of daily data. To understand here, you have it's a little tighter in terms of the point cloud. You don't have quite as many points. You have 365 instead of 8,760, but you can see the behavior more clearly. You can see this very prominent slope. You can almost imagine a regression line here. And up here at higher temperatures at 25 to 30 degrees, the slope seems to be a little less prominent, more of a flat situation here. Let's tease apart that difference between those two. And we're going to use a library called Seaborn. Seaborn you're going to learn a lot more in future episodes about this library. We're going to create a new visual column here because we notice after 25 degrees, from 25 degrees to the right, there seems to be less of a slope, more of a flat behavior here. So what we'll do is create a division of data. What we're looking at here is the amount of data greater than 25 versus below 25. So we have quite a bit of the data set above 25 degrees. Let's create a function that allows us to make that division. If X is less than 25, we'll return heating. And if it's above 25, we'll assume there's no heating. And you'll see here in a second why we use those labels. Let's run that cell. And let's create that new column called heating status, where we're doing on the temperature column, we're doing dot apply, and we're applying and looking at the temperature and making that new column according to what the temperature is outside. Let's look at our comparison file again. Now we have this new column called heating status. And what we can do with that heating status column is create this scatter plot diagram using Seaborn, which using an attribute called hue, adds a new colors. It basically defines the colors between above 25 and below 25 to show that it seems like we have a heating system which is proportional to the outside air temperature happening here as it gets colder, but at some point that heating system turns off, which is logical. That would happen around 25 degrees Celsius. So we've solidified quite a few of our knowledge of functions of pandas using this data set.